Okay, good morning everybody. Today we are going to start looking at mechanics. So the reason why in part we're doing this is if we were in lessons now, we would be looking at doing lots of revision, ready for mock exams. That would probably it would probably be a little bit too much in some ways to do revision for quite that many weeks, but we would be able to do other bits and bobs with it, like extension work and just making sure that we're as clear about what we need to do as possible, but also just as enthused about things as well. We can't really do that remotely, so instead what I thought I would do is start doing a mechanics minor. I had originally intended to do further pure technology with you next year. So the idea was that Mr. Clark was going to do extra pure, I was going to do further pure technology, and similar to this year, we'd split the main chunk of the pure up otherwise. So you'd have ended up with 4 minors at the end of the course. And if you sit 4 minors, and just to remind you how the course works, so there's the pure content, the core pure content, which is that big textbook you have. Altogether, that's half your A level. So the stuff for this year and next year is half your A level. And then the minors make up the other half. Each minor counts as a sixth. So if you do 4 minors, obviously you'll have a sixth too much, and the exam board just take your best 3 out of 4. So I think that's a pretty good way of dealing with, well, it's just a pretty good way of getting a better mark, but also actually a good excuse to learn some more maths as well. Further pure technology is quite a tricky thing to teach remotely. It requires lots of different computing packages, and ideally it would all have us having the same computer in front of us and me being able to get to you fairly quickly when you have problems with things, especially with things like running Python code where it's not obvious what you've done wrong and you need someone to look over your shoulder. So we're not going to do further pure technology, we're going to do mechanics instead. The first few weeks of this will be covering some of the stuff you'll cover in A level anyway. If you've done physics, you may have seen some of this already. So it's a bit irritating in some ways that you haven't done your mechanics in normal maths, but we can get through this stuff in fairly quick time, and we'll obviously only do the bits we need to do. And any proofs of things or where things come from, I'm not going to go through those bits. I'm just going to tell you facts for the A level stuff anyway, because I don't want to ruin it for your A level teachers next year when they want to explain this to you properly. So we're going to crack on with this mechanics stuff. I think we'll get this easily done before the summer, definitely. So if we were off all the time until then, we'll definitely get it done. If we come back early before the summer, obviously we're not quite sure what will happen with mocks and everything else, but I will make sure that we get through this mechanics stuff together. That means that altogether I'd have taught you obviously most of the pure for this year. I'd have taught you mechanics and I'd have taught you numerical methods, so it works out nearly as half the course. So you can half blame me if it doesn't go well next year. So let's crack on anyway. So kinematics. So what we're going to look at first of all today is a straightforward example. Here's someone on the edge of the cliff. I don't mind who you call it. Let's call it Duffers. Duffers is on the edge of the cliff and he's going to throw a ball up in the air, and then it's going to fall down to the ground, whatever the bottom here is. So let's just, for argument's sake, say that Duffers can't throw. That might actually be true. So let's say that distance from his hand to where the ball momentarily stops and then starts coming back down is 2 meters. If my book keeps moving, it's because one of my cats is nuzzling it. Stop it, Hattie. And then let's say then that's, 4's a bit rubbish, isn't it? 5 is much better. So 5 meters down from there to the ground. So there's a few things which we can talk about with this model, but the main thing which I want to do is just talk about some keywords which you guys will come across regularly during mechanics. So first of all, the word scalar. So scalar is something which just has magnitude. Just has magnitude. So an example of a scalar is speed. It doesn't matter if you're going forwards at 60 miles an hour or backwards at 60 miles an hour, your speed is 60 miles an hour. It only has magnitude, it does not have direction. A vector, so this is a scalar quantity, a vector quantity has magnitude and direction. And you've seen that in lots of vector work we've done. The vector has a size and it points in a certain direction. It's a little bit simpler in a lot of kinematics. So velocity is a common thing to use for a vector. Velocity has a magnitude, but it also has a direction as well. So if I was going forwards at 60 miles an hour, I would say my velocity is 60 miles an hour. And if I was going backwards at 60 miles an hour, given that I've defined that forwards being the positive direction, I would be saying that I'm going at a velocity of minus 60 miles an hour. So there's a direction forwards and backwards, and you can use plus and minuses to define those. So that's the fundamental difference between speed and velocity, and we've covered scalar and vector at the same time. So let's go back to this picture here and try and just figure out a few things. So one of the first things to note is that the ball starts at some initial position, and that initial position is quite useful because we generally will then talk about the rest of the problem from its starting position. The ball is thrown up, so let's say, and this is very useful in mechanics, drawing diagrams is just an absolute must. So let's say that this is the positive direction, upwards. So the ball starts with a positive velocity going up. It momentarily stops here, and then it has a negative velocity and it's getting faster and faster as it goes towards the ground. Speed-wise is the same as velocity going up, and it stops there, and as it comes back down, the speed is actually just the positive version of whatever the velocity would be, because the speed doesn't understand the idea of direction. Right then, next two things which we need to say which have a difference between them, even though they fundamentally look like they're the same thing. Okay, so the distance travelled for this particular scenario, and in mechanics when we draw diagrams like this we kind of ignore that there's any horizontal distance. We assume it's gone straight up and straight down, but because of the way that we draw things, it's easier to draw it like this to signify that it's gone up and it's come back down. We're totally ignoring left and right.
I need a ball for my shopping, please.
You need a ball for your shopping? Okay, see if you can find one. So the distance travelled, it goes up by 2 meters. It has 2 meters back down to here, and then it travels a further 5 meters. So that's 2 plus 2 plus 5, and altogether that's 9 meters. So nothing profound about that. However, it needs...
I didn't find any, Dada.
Oh, that's really bad news. Another word which is a lot like distance or distance travelled is displacement. Now, displacement deals with distances, but it deals with distances in a different way, similar to how velocity deals with speed in a slightly different way. So the displacement we normally measure from the starting point or starting position, but it could be measured from any position. If I think about the displacement from the starting position, it goes away from the starting position to 2 meters. So we'd say at this point its displacement is 2. Let's just add some things here. So A, B and C. So the displacement at A is equal to 2 meters. At B, we would say the displacement is 0 meters because it went up and then it's come back to where it was. Remember, yes, I've got a curve here, but assume it's gone straight up and straight down. So it went up, it came back to where it started, and at C, the displacement is 5 meters because it's 5 meters from where it started. Okay, so the distance travelled and displacement are similar in some ways and can be the same at certain points, for instance at A. However, as soon as things start turning back on themselves, then these two things end up differing. And one thing I've failed to mention is that displacement is a vector quantity, which must mean that this is minus 5 meters. So this is the positive direction, so that's 2 meters, 0 meters, minus 5 meters. So this is a scalar quantity, and this is a vector quantity. Okay, so a few more things we can start talking about here. We can say that the ball has some initial velocity when I throw it. Obviously, the moment it leaves my hand, it's travelling upwards with some velocity. So we'd say that u is the initial velocity. And we use the letter v for the final velocity. So for instance, and the final velocity can be wherever you choose it to be, depending on what you're interested in. So I could be saying my initial velocity is from when the ball leaves the hand, what's its final velocity at A? And at A, obviously, it's going to be 0. Or I could actually say my initial velocity is from A, what speed has it achieved, what velocity has it achieved by the time it gets to C? So that would, the speed here, u would be 0. At the bottom, v would be something larger than 0. So they're the two letters we use for initial and final velocity. S we use for displacement. T we use for time. And there's one last one which we haven't discussed so far. Obviously, once it leaves point A, it was travelling with a speed of 0. By the time it gets to point C, it's travelling a lot faster, which must mean it's accelerated. And we use the letter A for acceleration. And the acceleration, actually let's do the units before we do anything else. So all of these things have standard units assigned to them, and the standard units are meters per second, still meters per second. If you haven't seen this notation before, it is just meters per second. I've just written s to the minus 1. The displacement is measured in meters, the time is measured in seconds, and the acceleration is measured in meters per second squared, or ms to the minus 2. And acceleration to do with gravity. So acceleration due to gravity is equal to minus 9.8 meters per second to the minus 2. So I know you might be saying, well, that's surely deceleration. Well, acceleration is a vector quantity, so it has positive and negative directions. So in this particular example, as the ball goes up, there's an acceleration of minus 9.8 acting on it, hence why it slows down, slows down, slows down, slows down. And then hence why it speeds up this time, because it's minus 9.8, which is going in the negative direction, so it's going to get faster and faster and faster. Okay, so what we're going to do next is just have a look at some formulas that link all of these things together, and we're going to try and find what the speed of the ball is at c. Okay, so we're going to look at some formulas that link all these things together. Oh, no, we'll come back to that another time because that's quite funny. So these formulas have a special name. Most people call them the Suvat formulas, but their real title is constant acceleration formulae. If you wish to get chucked out of Miss User's lesson, the quickest way you can do it is by saying Suvat. She doesn't like that very much. Okay, the reason why people do call them Suvat is because S-U-V-A-T. It's just the way you can say them. So, the constant acceleration formulae. And it's really useful if you know these off the top of your head. And they don't take very long to learn, assuming that you write them down every time. So, there's 5 of them all together. We have V is equal to U plus AT. We've got S is equal to half of U plus V times T. We've got S equals to UT plus half AT squared. S is equal to VT minus half AT squared. And last but not least, number 5, we've got V squared equals U squared plus 2AS. Okay, so these are useful because all of them involve 4 of these and one's missing. So in this one, S is missing. In this one, A is missing. In this one, V is missing. In this one, U is missing. And in this one, T is missing. So as long as you've got 4 things, you should be able to work out what the 5th one is. And the way to work out which... Sorry, say that again. If you've got 3 things, you should be able to work out a 4th thing. And you pick the right one depending on what you don't know. So for instance, if you wanted to work out the final velocity and you haven't got time, but you've got the others, you'd use this one, for example. So let's use these quickly just to work some stuff out. So if we look back to our picture, and if we were interested to know what the speed is or the velocity is at c, we can do this by using one of our formulae. At the moment we've got all of the displacements in. We know what initial speeds are here and here. And we know what the acceleration is because the acceleration due to gravity is minus 9.8. Before anybody thinks or asks, we totally ignore air resistance. Air resistance is something which we could talk about, however that comes a lot later in mechanics and we won't be doing it in this course. So the thing that's missing at the moment is that we don't have any time. We don't know how long it takes to hit the bottom there. So what we need to do is find the formula which hasn't got time in. And the formula which hasn't got time in is the last one, v squared equals u squared plus 2as. So what we're going to do, and before you do any sort of kinematics question, write down what you know and what you want to find out. So we know the initial velocity is 0, and I'll come back to what I mean by that in a sec. And we know the final velocity is something that we want to find out. We know the acceleration is minus 9.8. Now, let's just have a look at the displacement for a sec. So, a common mistake someone might make here is saying the initial velocity is 0 and the displacement is minus 5 to get to c. And so they'd stick that into this equation saying 0, minus 5 for that one. However, that doesn't really actually tell the story properly. that just says I started here and I went backwards 5 meters. So yes, you're right in saying the displacement from this initial position is -5. However, if I plug that into my equation, that would be me trying to find the velocity as if I just dropped it from this position. So I need to think about a new position to measure my displacement from. So I'd measure my displacement from the top here because it's gone up, stopped. So it's stopped here, so its initial velocity is 0, and then it's got a displacement of -7 all the time it's accelerating under constant acceleration, and its obviously final velocity will be at c. So my displacement is going to be -7. Let's double check that I got that right. Yes, it is right. So I then write down my equation, v squared equals u squared plus 2as. I substitute in what I know. I don't know v. I know u is 0. And I know the acceleration is -9.8. And I know the displacement is -7. So if I work all that out, 2 times -9.8 times 7, 14 times 9.8, gives me 137.2. So I'm hoping for a velocity around about 12. So therefore the velocity is going to be the square root of this. However, it can be the positive or the negative square root. So because the ball is now traveling, or the stone or whatever it is now traveling in this direction, would say that the velocity is negative. So I take the negative square root of this, so negative 11.7, and it is really important that you stick your units in. Minus 11.7 meters per second. So time for you guys to have a go at a question. Here's an example. A coin is dropped from rest at the top of a building of height 12.25 meters and travels in a straight line. Find the time it takes to reach the ground and the speed of the impact. Just a point, if it says it's from rest, that means its initial velocity is 0. Have a think about which equation you're going to need and then see if you can work it out. So hopefully you've decided that this is the formula to use. That's because you don't know time, you do know displacement, you know the initial velocity, you know the acceleration, but you don't know the final velocity. So if I use this equation and plug it all in, I get 12.25 is equal to the initial velocity 0, so this becomes 0, plus half times minus 9.8 times t squared. So if I just make this a bit nicer, that gives me minus 4.9 t squared equals 12.25. Time has to be positive, and so when I divide by minus 4.9, I'm then going to square root it and take the positive square root. However, you may notice at this point that if you divide by minus 4.9, you're going to get a negative number here, which causes all sorts of problems when you take a square root. So this is a situation where you need to rethink possibly your picture. So this is why it's so important to do a picture before you start. So if I just drop a coin and it goes down this way, first of all I need to decide before I do anything else which is my positive direction. So it could be either up or it could be down. I'm going to go up because that seems like a standard thing to do. So the acceleration, minus 9.8, that's that way because it's going to get across the positive. However, the displacement is going to be minus 12.25 as well. And that's probably one of the most common errors that people make with these things. They don't make a diagram to start with. Or if they do make a diagram, they think of displacement as a scalar quantity. It isn't, it's a vector quantity. And so you need to ensure if you're dealing with vectors, and all of these things are vectors, the only scalar quantity in this is time, have they all got the correct sign? And obviously if you get to this sort of scenario and find out you're about to try and square root a negative number, obviously you've made some mistake there somewhere. So 12.25 divided by 4.9 equals whatever it equals, 5/2 apparently, and if I square root the answer, I get 1.58 seconds. So that's a really good question to make that point of these are vector quantities and you need to make sure they've got the right sign. If you decided this was the positive direction instead of going down, instead of going up, going down, then obviously this would be positive, this would be positive, so you would be square rooting a positive number. You get the same thing. It doesn't matter which way you pick the positive direction to be. Okay, so I'm going to send you one further example. It's example 1.8. And I'm going to also send you some exercises called exercise 1.2. Don't worry about what happened to exercise 1.1. And if you guys can try and do as much of that as possible, definitely questions 1 to 4, 1 to 5, they're the green ones. And as much of the yellow as possible. So as much of yellow as you have time for as possible. So I'll attach those on the VLE, those the scans of these things, so you can find those. I'll also stick them on class chats, and we'll carry on with some kinematics tomorrow, and we'll do something called variable acceleration, which sounds even more fun. Thanks very much, and I'll see you tomorrow. Bye.